In machine learning, support vector machines are supervised learning models with associated learning algorithms that analyze data and recognize patterns, used for classification and regression analyses. Given a set of training examples, each marked as belonging to one of two categories, an SVM training algorithm builds a model that assigns new examples into one category or the other, making it a non-probabilistic binary linear classifier. An SVM model is a representation of the examples as points in space, mapped so that the examples of the separate categories are divided by a clear gap that is as wide as possible. New examples are then mapped into that same space and predicted to belong to a category based on which side of the gap they fall on. In addition to performing linear classification, SVMs can efficiently perform a non-linear classification using what is called the kernel trick, implicitly mapping their inputs into high-dimensional feature spaces. Definition: more formally, a support vector machine constructs a hyperplane or set of hyperplanes in a high or infinite dimensional space, which can be used for classification, regression, or other tasks. Intuitively, a good separation is achieved by the hyperplane that has the largest distance to the nearest training data point of any class, since in general the larger the margin the lower the generalization error of the classifier. Whereas the original problem may be stated in a finite dimensional space, it often happens that the sets to discriminate are not linearly separable in that space. For this reason, it was proposed that the original finite dimensional space be mapped into a much higher dimensional space, presumably making the separation easier in that space. To keep the computational load reasonable, the mappings used by SVM schemes are designed to ensure that dot products may be computed easily in terms of the variables in the original space, by defining them in terms of a kernel function selected to suit the problem. The hyperplanes in the higher dimensional space are defined as the set of points whose dot product with a vector in that space is constant. The vectors defining the hyperplanes can be chosen to be linear combinations with parameters of images of feature vectors that occur in the database. With this choice of a hyperplane, the points in the feature space that are mapped into the hyperplane are defined by the relation. Note that if becomes small as grows further away from, each term in the sum measures the degree of closeness of the test point to the corresponding database point. In this way, the sum of kernels above can be used to measure the relative nearness of each test point to the data points originating in one or the other of the sets to be discriminated. Note the fact that the set of points mapped into any hyperplane can be quite convoluted as a result, allowing much more complex discrimination between sets which are not convex at all in the original space. History: the original SVM algorithm was invented by Vladimir N. Vapnik and the current standard incarnation was proposed by Corinna Cortez and Vapnik in 1993 and published in 1995. Motivation: classifying data is a common task in machine learning. Suppose some given data points each belong to one of two classes, and the goal is to decide which class a new data point will be in. In the case of support vector machines, a data point is viewed as a p-dimensional vector, and we want to know whether we can separate such points with a dimensional hyperplane. This is called a linear classifier. There are many hyperplanes that might classify the data. One reasonable choice is the best hyperplane is the one that represents the largest separation, or margin, between the two classes. So we choose the hyperplane so that the distance from it to the nearest data point on each side is maximized. If such a hyperplane exists, it is known as the maximum margin hyperplane and the linear classifier it defines is known as a maximum margin classifier. Or equivalently, the perceptron of optimal stability. Linear SVM, given some training data, a set of endpoints of the form where the E is either 1 or a 1, indicating the class to which the point belongs. Each is a p-dimensional real vector. We want to find the maximum margin hyperplane that divides the points having from those having. Any hyperplane can be written as the set of points satisfying, where denotes the dot product and the normal vector to the hyperplane. The parameter determines the offset of the hyperplane from the origin along the normal vector. If the training data are linearly separable, we can select two hyperplanes in a way that they separate the data and there are no points between them, and then try to maximize their distance. The region bounded by them is called the margin. These hyperplanes can be described by the equations. And by using geometry, we find the distance between these two hyperplanes is, so we want to minimize. As we also have to prevent data points from falling into the margin, we add the following constraint, for each either of the first class, or of the second. This can be rewritten as, we can put this together to get the optimization problem, minimize. Subject to primal form, the optimization problem presented in the preceding section is difficult to solve because it depends on W, the norm of W, which involves a square root. Fortunately, it is possible to alter the equation by substituting W without changing the solution. This is a quadratic programming optimization problem. More clearly, subject to by introducing Lagrange multipliers, the previous constraint problem can be expressed as, that is, we look for a saddle point. In doing so, all the points which can be separated as do not matter since we must set the corresponding to 0. This problem can now be solved by standard quadratic programming techniques and programs. The stationary Karushia-Kiner-Tucker condition implies that the solution can be expressed as a linear combination of the training vectors. Only a few will be greater than 0. The corresponding are exactly the support vectors, which lie on the margin and satisfy. From this one can derive that the support vectors also satisfy, which allows one to define the offset. In practice, it is more robust to average over all support vectors. Dual form, writing the classification rule in its unconstrained dual form reveals that the maximum margin hyperplane and therefore the classification task is only a function of the support vectors, the subset of the training data that lie on the margin. Using the fact that and substituting, one can show that the dual of the SVM reduces to the following optimization problem, maximize. Subject to and to the constraint from the minimization in. Here the kernel is defined by can be computed thanks to the terms biased and unbiased hyperplanes. For simplicity reasons, sometimes it is required that the hyperplane pass through the origin of the coordinate system. Such hyperplanes are called unbiased, whereas general hyperplanes not necessarily passing through the origin are called biased. An unbiased hyperplane can be enforced by setting in the primal optimization problem. The corresponding dual is identical to the dual given above without the equality constraint. Soft margin. In 1995, Corinna Cortez and Vladimir N. Vapnik suggested a modified maximum margin idea that allows for mislabeled examples. If there exists no hyperplane that can split the yes, and no examples, the soft margin method will choose a hyperplane that splits the examples as cleanly as possible, while still maximizing the distance to the nearest cleanly split examples. The method introduces non-negative slack variables, which measure the degree of misclassification of the data. The objective function is then increased by a function which penalizes non-zero, and the optimization becomes a trade-off between a large margin and a small error penalty. If the penalty function is linear, the optimization problem becomes subject to. This constraint and along with the objective of minimizing can be solved using Lagrange multipliers as done above. One has then to solve the following problem with dual form, maximize. Subject to and. The key advantage of a linear penalty function is that the slack variables vanish from the dual problem, with a constant c appearing only as an additional constraint on the Lagrange multipliers. For the above formulation and its huge impact in practice, Cortez and Vapnik received the 2008 ACM Paris-Cain-Lakis Award. Nonlinear penalty functions have been used, particularly to reduce the effect of outliers on the classifier, but unless care is taken the problem becomes non-convex, and thus it is considerably more difficult to find a global solution. Nonlinear classification. The original optimal hyperplane algorithm proposed by Vapnik in 1963 was a linear classifier. However, in 1992, Bernhard E. Boser, Isabel M. Guyon and Vladimir N. Vapnik suggested a way to create nonlinear classifiers by applying the kernel trick to maximum margin hyperplanes. The resulting algorithm is formally similar, except that every dot product is replaced by a nonlinear kernel function. This allows the algorithm to fit the maximum margin hyperplane in a transformed feature space. The transformation may be nonlinear and the transformed space high-dimensional. Thus, though the classifier is a hyperplane in the high-dimensional feature space, it may be nonlinear in the original input space. If the kernel used is a Gaussian radial basis function, the corresponding feature space is a Hilbert space of infinite dimensions. Maximum margin classifiers are well regularized, so the infinite dimensions do not spoil the results. Some common kernels include polynomial, Gaussian radial basis function, 4. Sometimes parametrized using hyperbolic tangent, for some, and the kernel is related to the transform by the equation. The value W is also in the transformed space, with dot products with W for classification can again be computed by the kernel trick, that is. However, there does not in general exist a value W such that properties, SVMs belong to a family of generalized linear classifiers and can be interpreted as an extension of the perceptron. They can also be considered a special case of Tyche-Kernel regularization. A special property is that they simultaneously minimize the empirical classification error and maximize the geometric margin. Hence they are also known as maximum margin classifiers. A comparison of the SVM to other classifiers has been made by Mayer, Leisch and Hornig. Parameter selection. The effectiveness of SVM depends on the selection of kernel, the kernel's parameters, and soft margin parameter Ca. Common choice is a Gaussian kernel, which has a single parameter I cubed. The best combination of C and I cubed is often selected by a grid search with exponentially growing sequences of C and I cubed, for example. Typically, each combination of parameter choices is checked using cross-validation, and the parameters with best cross-validation accuracy are picked. The final model, which is used for testing and for classifying new data, is then trained on the whole training set using the selected parameters. Issues, potential drawbacks of the SVM are the following three aspects: uncalibrated class membership probabilities. The SVM is only directly applicable for two class tasks. Therefore, algorithms that reduce the multiclass task to several binary problems have to be applied. See the multiclass SVM section. Parameters of a solved model are difficult to interpret. Extensions, multiclass SVM. Multiclass SVM aims to assign labels to instances by using support vector machines, where the labels are drawn from a finite set of several elements. The dominant approach for doing so is to reduce the single multiclass problem into multiple binary classification problems. Common methods for such reduction include building binary classifiers which distinguish between one of the labels and the rest or between every pair of classes. Classification of new instances for the one versus all case is done by a winner-takes-all strategy, in which the classifier with the highest output function assigns the class. For the one versus one approach, classification is done by a max wins voting strategy, in which every classifier assigns the instance to one of the two classes, then the vote for the assigned class is increased by one vote, and finally the class with the most votes determines the instance classification. Directed acyclic graph SVM, error-correcting output codes. Kramer and Singer proposed a multiclass SVM method which casts the multiclass classification problem into a single optimization problem, rather than decomposing it into multiple binary classification problems. See also Lee, Lin and Wachber. Transductive support vector machines. Transductive support vector machines extend SVMs in that they could also treat partially labeled data in semi-supervised learning by following the principles of transduction. Here, in addition to the training set, the learner is also given a set of test examples to be classified. Formally, a transductive support vector machine is defined by the following primal optimization problem: minimize, subject to, and. Transductive support vector machines were introduced by Vladimir N. Vapnik in 1998. Structured SVM. SVMs have been generalized to structured SVMs, where the label space is structured and of possibly infinite size. Regression. A version of SVM for regression was proposed in 1996 by Vladimir N. Vapnik, Harris Drucker, Christopher J. Sebergs, Linda Kaufman and Alexander J. Smolar. This method is called support vector regression. The model produced by support vector classification depends only on a subset of the training data, because the cost function for building the model does not care about training points that lie beyond the margin. Analogously, the model produced by SVM depends only on a subset of the training data, because the cost function for building the model ignores any training data close to the model prediction. Another SVM version known as least squares support vector machine has been proposed by Sukens and van der Waal. Interpreting SVM models, the SVM algorithm has been widely applied in the biological and other sciences. Permutation tests based on SVM weights have been suggested as a mechanism for interpretation of SVM models. Support vector machine weights have also been used to interpret SVM models in the past. Post-hoc interpretation of support vector machine models in order to identify features used by the model to make predictions is a relatively new area of research with special significance in the biological sciences. Implementation: the parameters of the maximum margin hyperplane are derived by solving the optimization. There exist several specialized algorithms for quickly solving the QP problem that arises from SVMs, mostly relying on heuristics for breaking the problem down into smaller, more manageable chunks. A common method is Platt's sequential minimal optimization algorithm, which breaks the problem down into two-dimensional subproblems that may be solved analytically, eliminating the need for a numerical optimization algorithm. Another approach is to use an interior point method that uses Newton-like iterations to find a solution of the Karushia-Kiner-Tucker conditions of the primal and dual problems. Instead of solving a sequence of broken-down problems, this approach directly solves the problem as a whole. To avoid solving a linear system involving the large kernel matrix, a low-rank approximation to the matrix is often used in the kernel trick. The special case of linear support vector machines can be solved more efficiently by the same kind of algorithms used to optimize its close cousin, logistic regression. This class of algorithms includes subgradient descent and coordinate descent. The general kernel SVMs can also be solved more efficiently using subgradient descent, especially when parallelization is allowed. Kernel SVMs are available in many machine learning toolkits, including LibSVM, MATLAB, SVMLite, scikit-learn, Shogun, Weka, Shark, kernel machines and others. Applications: SVMs can be used to solve various real-world problems. SVMs are helpful in text and hypertext categorization as their application can significantly reduce the need for label training instances in both the standard inductive and transductive settings. Classification of images can also be performed using SVMs. Experimental results show that SVMs achieve significantly higher search accuracy than traditional query refinement schemes after just 3 to 4 rounds of relevance feedback. SVMs are also useful in medical science to classify proteins with up to 90% of the compounds classified correctly. Handwritten characters can be recognized using SVM, see also, in situ adaptive tabulation, kernel machines, Fisher kernel, Platt scaling, polynomial kernel, predictive analytics, regularization perspectives on support vector machines, relevance vector machine, a probabilistic sparse kernel model identical in functional form to SVM, sequential minimal optimization, Winnow, references. External links: Bergs, Christopher J.C. A tutorial on support vector machines for pattern recognition, data mining and knowledge discovery to 167, 1998, www.kernel-machines.org, Tenomo, KSVM tutorial using spreadsheet visual introduction to SVM. www.support-vector-machines.org, videolectures.net, Karat Sogler, Alexandros A.L. Support vector machines in R, Journal of Statistical Software April 2006, Volume 15, Issue 9, LibSVM. LibSVM is a popular library of SVM learners. LibLinear. LibLinear is a library for large linear classification including some SVMs. Shark. Shark is a C++ machine learning library implementing various types of SVMs, glib is a C++ library for working with kernel methods and SVMs. SVM Lite is a collection of software tools for learning and classification using SVM. SVM.js Live Demo is a GUI demo for JavaScript implementation of SVMs, bibliography, Theodoridis, Sergios, and Koutroumbas, Konstantinos. Pattern Recognition, 4th edition, Academic Press, 2009, ISBN 978-1-59749-272-0, Christiani, Nello. And Shaw-Taylor, John. An Introduction to Support Vector Machines and Other Kernel-Based Learning Methods, Cambridge University Press, 2000. ISBN 0-521-78019-5, Huang, T. Ming. Kekman, Vyacheslav. And Kopriva, Ivica. Kernel-based algorithms for mining huge data sets, in supervised, semi-supervised, and unsupervised learning, Springer Verlag, Berlin, Heidelberg, 260 ppA 96 Illis, hardcover, ISBN 3-540-31681-7, 2, Kekman, Vyacheslav. Learning and Soft Computing Euro Support Vector Machines, Neural Networks, Fuzzy Logic Systems, The MIT Press, Cambridge, Massachusetts, 2001. 3, Paragraph LKOPF, Bernhard. And Smoller, Alexander J. Learning with Kernels, MIT Press, Cambridge, Massachusetts, 2002. ISBN 0-262-19475-9, Paragraph LKOPF, Bernhard. Bergs, Christopher J.C. And Smoller, Alexander J. Advances in Kernel Methods, Support Vector Learning, MIT Press, Cambridge, Massachusetts, 1999. ISBN 0-262-19416-3. 4, Shaw-Taylor, John. And Christiani, Nello. Kernel Methods for Pattern Analysis, Cambridge University Press, 2004. ISBN 0-521-81397-2, Steinwert, Inko. And Chris Mann, Andreas. Support Vector Machines, Springer Verlag, New York, 2008. ISBN 978-0-387-77241-7, Tan, Peter Jing. And Dow, David L. MML Inference of Oblique Decision Trees, Lecture Notes in Artificial Intelligence 3339, Springer Verlag, pp 1082-1088 and actually incorporates probabilistic support vector machines in the leaves of decision trees. Vapnik, Vladimir N. The Nature of Statistical Learning Theory, Springer Verlag, 1995. ISBN 0-387-98780-, Vapnik, Vladimir N. And Kotz, Samuel. Estimation of Dependencies Based on Empirical Data, Springer, 2006. ISBN 0-387-30865-2, 510 pages. This is a reprint of Vapnik's early book describing philosophy behind SVM approach. The 2006 appendix describes recent development. Fradkin, Dmitry. And Muchnik, Elia. Support Vector Machines for Classification in Abelo, J. And Karmad, G. Discrete Methods in Epidemiology, DIMAC Series in Discrete Mathematics and Theoretical Computer Science, Volume 70, ppA 13 Euro 20, 2006. 7. Succinctly describes theoretical ideas behind SVM. Bennett, Kristen P. And Campbell, Colin. Support Vector Machines, Hype or Hallelujah. SIGKDD Explorations, 2, 2000, 1 Euro 13. 8. Excellent Introduction to SVMs with Helpful Figures. Ivan Sayuk, Ovidiu. Applications of Support Vector Machines in Chemistry, in Reviews in Computational Chemistry, Volume 23, 2007, ppA 291 €400. Reprint available. 9. Catanzaro, Brian. Sundaram, Narayanan. And Kitzer, Kurt. Fast Support Vector Machine Training and Classification on Graphics Processors, in International Conference on Machine Learning, 2008, 10, Campbell, Colin. And Iming. Learning with Support Vector Machines, 2011, Morgan and Claypool. ISBN 978-1-60845-616-1. 11.